Hello and welcome to a new video presented by Telescope-Service. My name is Thorsten, and in this video I want to give you some insights about autoguiding. So first of all, why do we need autoguiding? Well, the purpose of astrophotography is to produce pinpoint sharp images. So the focusing is very important, of course, but also that the tracking of your mount works properly. Especially when doing long-time astrophotography, you have to ensure that the mount is working point on and properly. But a normal, let's say a normal telescope mount, like a German equatorial mount like this one, has some intrinsic errors. The first one is it uses a worm wheel to create a gear reduction. From the motor to the mount, there's a worm gear integrated with a reduction of, let's say, 1/100th or 1/200th. And this worm does not rotate uniform. It is sometimes fast and sometimes slower within one rotation. And that produces an error that is called periodic error, because it occurs periodic, as the name says. That's the first issue you want to overcome. That problem is well known for many years, so the mounts, especially electronic mounts, have a feature integrated which is called periodic error correction, where you can apply correction pulses, but with a astro camera there are more convenient ways to do it. The second thing is your mount may have some mechanical imperfections. That means it may just move not very good. There may be some flaws. Maybe there's some dirt in it, or the gear is just not working properly. That's the second problem. And the third problem is the alignment to the celestial pole. You can't really overcome this with autoguiding, but you can improve the results. So these three problems are addressed now with autoguiding, and we want to solve them. Now let me just explain you very quickly the principle how autoguiding works. For example, you have a telescope where a primary camera is attached in the back, and you want to produce proper photos with it. So for example, with this rigid criterion here, you have to expose at least 2-3 minutes, maybe 5 minutes or something like that. And over this period, the mount has to move absolutely perfect with the stars. And the idea is now to attach a second camera, may it be as a second scope or in addition to your primary camera, to do very short exposures with that second camera in the range of 1 to 5 seconds. This camera captures images from nearly the same field, the same star field in the sky, and now it can see within that short time period where the mount is moving to. Is there a deviation to the previous position of the image? And if so, the software, the camera, creates correction pulses that are sent to the mount, and then the mount will correct these wrong movements to be again point on as it should be. So this was a very rough and quick explanation, but I hope you can follow the idea of it. By the way, if you have any questions about the technique, about the equipment, about the software that I'm covering here, feel free to drop a comment below the video. Of course, we'll try to answer that. Now let me explain what equipment options you have to use autoguiding. The first way to do it is with a second scope. You attach a so-called guide scope, something like this, to your primary telescope. In principle, this is just a finder scope. This one here has 50mm diameter, approximately 200mm focal length, but it has not an eyepiece in the end, but it has a helical focuser. And here in that helical focuser you put in your camera, your guide camera, and this system here will now create these short exposures that are used then to correct the movement. So with this guide scope you have the big advantage that this is a super simple setup. So it is separated from your primary scope. That means you can exchange the camera, you can change focus here. Everything is possible without interfering the autoguiding here. but this combination has its limits. So we use a technique that is called subpixel guiding. What this means, I cover it in a minute when I'm talking about the software, but I can tell you that the ratio of the focal lengths of both systems should be in a specific range. And I would say 1/10 is the maximum. For example, this telescope here has 1300 mm focal length and this one 200, so that's well in the range. There should be no problem. If this gets bigger, for example, you try to guide a very big telescope, a very long refractor with only a guide scope, that can be a problem. There is another little drawback with this setup. With such a lightweight and small telescope, this is not a problem. But when you use a very big guide scope, for example, you have a refractor, some Fraunhofer big 100 mm refractor or something like that, then the problem is that these two telescopes will bend against each other, something that is called differential flexure. And the result is that your guiding may be point on, because the guide camera can correct the position, but the primary telescope bends slightly. Only arcseconds, but this is enough to create elongated stars all over the field and overall images. This is highly depending how the telescope is orientated in the sky and where it's moving to, but this can happen, and the only way to overcome this is by creating a very, very rigid combination, a very rigid connection between these two telescopes, which is not that easy. So I would recommend using only a small guide scope. There are also smaller guide scopes available, 30 mm diameter. It's also working well for small telescopes. I would say every Newtonian telescope up to 10 inch is guidable with such a scope. There's no problem with it. You may have recognized with this setup here, you have a little problem, and this is you lose the position for your finder scope. If you want to find the objects visually by looking through the finder scope, this is not possible here. But therefore we have a little tool available also in the shop, and this is this Y bracket here. You just mount this bracket on the telescope, and then you have two connections, and you can use one of them for the guide scope and then the second one for the finder scope. Okay, now if you have a very big telescope, for example a very long refractor or bigger Ritchie-Chrétien telescopes, or you just want to ensure that you have the best possible quality of your images, then the way to go is a so-called off-axis guider. An off-axis guider is a very simple piece of equipment. For example, one like this. This is this so-called TSOEG9. This is one of the shortest off-axis guiders that are available. And the principle is very simple. We have here a little prism integrated on the very corner of that aperture here. And that prism reflects a very small portion of the off-axis light, that's why they're called off-axis guider, out here 90 degrees into that holder, and here, just a moment. Now let's just quickly assemble an image train here. So with the off-axis guider we use, so we have a one-shot color camera. So we use a filter drawer with an L Pro filter, a camera. That's an older one here, but of course it's possible with all cameras. They may be out there. And then for that telescope we normally use a reducer, because it has a native focal ratio of f9, which is pretty slow. So this is our whole image train, and this image train comes now in the back here in the focuser. Now we can be sure that there's no flexure here, and we use, and that's the cool thing, we use the current focal length of the telescope to guide the frame, to guide the telescope in the mount. And together with this subpixel guiding, this works also on fractions of a pixel, which is pretty important, because if you can only detect the movement between one and another pixel, that would be too rough. That would be not precise enough. Now, let's talk also about some drawbacks of that way to do it. The first one is you have to take this off-axis guider into account when calculating your image train. The length is changing, of course. You can't just put in an off-axis guider and hope that will still work. So this one here takes 9mm of optical path. You have to take that into account. There are others available, for example, here an older model, the TS-OAG27. This is not sold anymore. The current device is called TS-OAG16, which has 16mm of optical path. And there are also different diameters available. For example, all these ones here have, for example, an M48 thread and a T thread here for direct camera connection. But they are also available with M68, for example, as a very large off-axis guider if you use full-frame cameras. And what you also can do, if you want to have it complete and you don't want to fiddle around with all these spacing and so on, you can grab it from one manufacturer. For example, ZWO offers the whole setup. They offer an off-axis guider, a filter drawer, the camera and a guide camera. And because all the lengths and distances are known, you can get rid of that holder here on the top. So then the camera can be screwed on directly, which is pretty cool and even creates an even better connection between all the optical elements. And the last point about this off-axis guiding, there can be an issue, especially if you have a telescope with a long focal length, something like this here, or even longer focal length. You can use only a very small portion of the light. So the field of view of this guide camera is very narrow, only a couple of arc minutes. And the problem now is that you have regions in the sky where just no guide star is visible. You can't reach a guide star even with 5 or 10 second exposures. You can't reach them. And this can be a real problem if your primary sensor is too small. So the only way to get around this problem is to move the telescope very slightly, carefully, a couple of arc minutes in every direction to look for a guide star. Now the problem is, if your primary sensor is very small, then your object that you want to capture may be out of view, or let's say in one of the corners of the view. And that can be really annoying. You should take care of that. That can happen. It happened to me also, especially in the, let's say, starless regions, in the galaxy regions. That can be an issue. What you also can try is to rotate the camera together with the off-axis guider, just to bring the off-axis guider into a different position in the sky. Maybe there is a star then visible. Well, now we talked much about equipment, but just a camera can't do the guiding for you. This is just not possible. You have to use some software or additional computer to create these correction pulses. So the first way that I want to explain is by a PC with a software. And currently the most used software is so-called PhD guiding, or more specifically PhD2 guiding. It is a free software that you just can download and install and you're good to go. A really powerful and nice tool that nearly everyone uses for guiding. There are other solutions available, for example MetaGuide, which is a much more powerful software which can also do different things. So I would rely on PhD2, which works well, and it offers you also some more features like support for polar alignment and so on. Here we have a screenshot of PhD2. Let me just quickly explain the things that you see here. So first we have our imaging area, where you can see the image that the AutoGuide camera produces, and this is also used for focusing. In the lower section you see a trend graph. There you can see the deviation that is measured and the correction pulses that are sent to the mount to correct this deviation. And on the right side, on the top, that's pretty important. This is the guide star where the software is currently guiding on, and it's the star profile. So there's just a cut through the star, and here you can see how the star shape is looking, and it should look like a Gaussian curve. That's always the best. If there are some gaps or something, the shape is just not good, not round, then you have to correct your guide camera or the prism. And here I can also show you what the sub-pixel guiding means. So the software does not rely on a single position of one pixel or one star. No, it calculates the Gaussian curve, it interpolates it, and then it can calculate the center, the brightest point of that curve, very precise, to fractions of a pixel. And this is why this whole idea of the sub-pixel guiding is working so good. PhD2 also uses multiple stars, if there are multiple stars in your field, especially with a guide scope, and then it averages multiple stars, which makes the correction smoother, so it will not overcorrect that easily. This PhD2 software requires a PC, as said. But maybe you have a mobile setup with a DSLR camera, for example, and then you don't want to carry a PC with you around, but there's also a solution for that. To be honest, there are multiple solutions. Let's start with the most easy one. And this is this device here. This is the so-called Engine from Lacerta. This is a little computer that does all this guiding for you. So it comes with a very tiny and lightweight camera with a USB connection on the side. So this camera is used as guide camera. So it comes here into your guide scope. And now this PC does all the corrections for you. First it calibrates itself, that it knows where it has to move for a specific correction, and then it starts capturing images and it will correct the telescope movement. It has an ST4 port which goes directly to the mount. The ST4 interface is the common standard for a guiding interface. It sends just electrical pulses for all 4 directions, but you don't have any more control over it. It just works and then it's good. If not, it can be a problem. Therefore, another solution is the controlling by software, by a software protocol like PhD2 does, and this is by ASCOM pulse guiding. So then the software sends a command which tells the mount move 100 milliseconds to a direction or 10 milliseconds in another direction. So nowadays I would always recommend to use that ASCOM pulse guiding because it offers you more control, or it offers the software more control over the guiding process. Maybe now you want to do something more with a PC on your telescope. The next option would be, for example, the ASI Air. I'm pretty sure you already heard of it. This is also a little mini computer which is specifically designed for astrophotography. It comes from ZWO, so to be honest, you have to use a ZWO camera to work with. It can control other mounts, this is no problem, but the camera equipment has to be from ZWO. It is what it is. But this one works like a charm because it's dedicated to their cameras, it works very well, and it offers you more than just guiding. So there is a clone of PhD2 integrated. Guiding is the most easy part of it, but you can do much more. You can control the whole capturing process. So you can capture images, align them, stack them together. You can also calibrate them in that ASI Air to have a full calibrated image coming out of it, which makes automation super easy, especially for mobile setups on your balcony. These are great, or in your backyard. When talking about astrocomputers, I want to show you also the upper end of astrocomputers that is available. And this is the so-called Eagle from Primaluz Lab. So this is definitely a different story, but I think it's a good idea to show you what you also can do with astrocomputing. So this one is a real industrial PC, comes in a very big metal housing, also a very rigid housing with many threaded holes on it. That means it can be really integrated in your setup. You can also put dovetails onto it, so you can integrate it between the mount and the telescope if you want. It offers you power ports, switchable power ports for different equipment, and of course also USB ports, a couple of them. They are also switchable. That's pretty important for remote astrophotography, that you can switch on and off an USB port electronically, so you don't have to plug a cable if something goes wrong. Offers of course Wi-Fi connection and uses a powerful processor in it, so you can also do image processing in the software. And it runs Windows 11, so all the known software, all the ASCOM standard is available for that Eagle. Okay, that's all that I can tell you about autoguiding. I hope it was informative for you. I hope I can clarify some things and to give you some ideas how to proceed with your equipment selection. Thank you very much for viewing, and see you next time. Bye bye.